Good morning, good afternoon, or good evening, wherever you are listening to this. Thanks for joining this presentation about the stability of XBLOCPLUS armor layers after initial damage. My name is Pieter Bakker. I'm going to give this presentation, and it's basically mainly the work of Timon de Hoop, who did most of the work, so thanks a lot, Timon, and by Marcus Moutré. In this presentation, I will give a short introduction about XBLOC and XBLOCPLUS. I will go a bit more in depth about the resilience to climate change of the XBLOCPLUS. Then we'll come to the research objective. Then we'll talk about the model test setup and the results from the test. And we'll finalize with conclusions. XBLOC on the left-hand side is our concrete armor block, which we have been using since 2003. And XBLOCPLUS on the right-hand side is the new block that we have developed between 2015 and 2018. So why should you use the XBLOCPLUS? Well, there's many reasons. We've tried to summarize the main advantages in this sheet, but in this presentation the main topic to talk about is the resilience to climate change. So that's what I want to talk about a little bit more. If you design a breakwater or shore protection right now, you probably use a different design wave height than you would have used 20 years ago for the same structure. The reason for that is that the wave climate is changing due to climate change. Therefore, it's very difficult to make a good prediction of your design wave height, especially for structures with a long lifetime, maybe 30 years, maybe even up to 100 years. So it is important that you use a design which has a resilience for higher waves than you currently anticipate. In the graph on the right-hand side, we have schematized the physical model test that we've performed for XBLOC and XBLOCPLUS, and the stability number, the design stability number that we've concluded from these tests. I'm going to take out some data to make it a bit more clear. On the horizontal axis, you see the stability number, and on the left-hand side, a low number means that you have a big block for a low wave, and on the right-hand side, the high numbers, that means that you have a small block for a very high wave. The Gauss curve shows where for XBLOC we observe start of damage in the physical model tests. And you can also see the design stability number of 2.77 or KDE 16, and this blue arrow signifies the resilience in the design with XBLOC, or the safety margin that's in the design. And I'm going to add the orange dots, which are all physical model tests with XBLOCPLUS without any damage. And in fact, we've not been able to create damage in our own wave flume because the waves cannot be made high enough for the model blocks. But also the other laboratories that we visited, we did not get damage to the armor layer. So we've plotted this hypothetical Gauss curve for XBLOCPLUS start of damage. It could be further to the right, but it is at least very safe to say that it is further to the right than it is for XBLOC. And nonetheless, with our design stability number for XBLOCPLUS, we went to the left. We've chosen 2.5 stability number, or a KD of 12, which results in an orange arrow, the resilience, which is far greater, and it's in fact far greater than for XBLOC, but also for other blocks in the market. Having a large resilience also has impact on the maintenance need during the lifetime of a structure. We have done a life cycle analysis for two structures, which are shown in this sheet. On the left-hand side at the bottom, you see a rock shore protection, which was designed by a client, and on the right-hand side at the bottom, an equivalent XBLOCPLUS cross-section, so for the same design wave height and for the same overtopping. And in the middle, at the bottom, you see the design wave climate. The blue line shows the present-day wave climate, and the gray line shows the predicted design wave climate in 100 years. We've used these wave climates to determine every year the expected damage in the armor layer during a Monte Carlo simulation. And we've summarized that in the table at the top. And there you can see that based on this wave climate and these structures, the rock structure, you can expect to need one maintenance repair during the lifetime of the structure based on the current wave climate. But based on the future wave climate, it would need 3 repair sessions during the lifetime of the structure. On the other hand, the XBLOCPLUS structure has so much resilience that both for the current wave climate and for the future wave climate, no maintenance is required. Another aspect which is very important for the reliability and the resilience of the structure is the robustness of the blocks. The XBLOCPLUS is a very bulky unit which can take very large forces, so it's a very reliable block also from that perspective. So this brings me to the research question. What would happen to an XBLOCPLUS armor layer if for some reason there is damage? Possible causes that we can think of how you could get damage to individual units would be a fabrication defect, which appears after block placement, or maybe the contractor places the block in a very rough manner and there's breakage of the block which is not noticed, or possibly impact of floating objects. For that purpose, we have done physical model tests. So Timon did lots of work for this. Physical model tests with XBLOCPLUS model blocks of 58 grams. They have a design wave height of about 10 centimeters, and we've done tests starting at 80% of the design wave height, reaching up to 150% of the design wave height. Each test series was 1,000 waves. We did wave steepnesses of 0.02 and 0.04. And we did 6 configurations of armor blocks with broken blocks in the slope. And I will show. This slide shows the configurations that we tested, where orange shows the broken blocks and black shows the blocks which were left out. In this sheet you see a cross-section of the model as it was built, and you also see on the right hand side how we divided it into sections to analyze the settlements. You see a short video impression of test 7B, or at 150%, so already at 140% one block was removed. And now and then you can see some underlayer rock being extracted through the gap around the waterline. Looking at extractions, the tests were in fact not so exciting. Only in test 7B2 there was an extraction at 140% wave height. And in test 7B4 there was an extraction at 150% wave height. And since this was the last test, Timon continued with one more test after that, which was twice the design wave height. And in that test he had another 3 blocks displaced or extracted. And this is what it looks like. This was 7B2, the way the model was built up, and then we click through and we see how the model behaves. Now we're after 120%, 130, and then at 140 you see the block displaced in the middle. And then this is what it looks like after test 150. And you can also see quite a lot of underlayer material at the toe of the breakwater. And this is test 7B4. We start at 130% test, and then we move on. And then here you can see that during the 150% test, the same block was displaced. And then this is the situation after the 200% test. And the 2 more blocks in the middle have settled into the gap, which we consider an extraction. And there's 1 more block at the toe. And again, you can see quite a lot of underlayer material at the toe of the structure. We also looked at settlements. As I said before, we looked at 4 zones, starting at 1 at the top, 2 and 3, and then 4 towards the toe of the structure. This is an impression of the settlements in test 0-4, and unfortunately it was noted that the toe of the structure was not completely stable in this test. So there were quite some settlements, and you can also see that the settlements at the toe were largest. Then this is test 2-4. And in this test with only the broken blocks, settlements are in fact quite small, and still there are some settlements towards the toe of the structure. So also in this test, the toe was still not completely stable. And here test 1-4, where really not a lot happened, very small settlements. Then we go to test 6, where the blocks were extracted by hand before the test. And you can see that this really has a little effect on the settlements. Then we go to the bigger damaged areas as they were built into the model. And you can see that this leads to slightly bigger settlements. And then test 7B2 with one of the blocks extracted during the 140% test. And the settlements are still relatively small. The biggest settlement is the block at the side, 19% of the N. And 7B4. Similar behavior, 1 block extracted at the 150% test, and the settlements are in the range of 7 to 10% of DN. So if you look at the settlements divided over the sections, you can see in this sheet the settlements of all the tests combined, but the test 0 distorts the figure a little bit. So if I take that one out, you can see that most tests at the biggest settlements in section 2, which is between the still water level and one design significant wave height above. And the sediments are in the order of 3 to 10% of DN. So that brings me to the summary of the test results. If we look at all the tests that we have performed, we can see that if you have one damaged block or one missing block in your slope, this doesn't lead to movements or settlements of the blocks around it. It also doesn't lead to significant rock extractions. We saw on occasion 1 or 2 rocks being extracted. Then there were some clusters of 3 or 4 damaged or missing blocks. Also, they had limited impact. But if you look at the clusters of 6 damaged or missing blocks, we can see that they lead to moderate settlements of the blocks that are surrounding the damaged areas. And they also lead to underlayer rock extractions. And this occurs typically for waves above 100 or 120% of the design wave height. And we also see that these clusters lead to extraction of an uninterlocked block for wave heights above 130% of the design wave height. So this brings me to the following conclusions. XBLOCPLUS provides very high resilience to wave heights that exceed the design wave height. In the physical model test that we have performed earlier on, we've seen that no damage occurs even for wave heights up to 225% of the design wave height. Damaged armor units are very unlikely because the block is very robust and has a very high hydraulic stability, and also no rocking was observed in the physical model tests. Physical model tests that we have done with intentional damage in the armor layer shows that no further damage occurs even for wave heights up to 130% of the design wave height. This is relevant because it tells you that if you would have damage in an XBLOCPLUS project, you can wait with the repair until the next summer season rather than do a hasty emergency repair in the winter conditions. And that brings me to the last slide. If there's any questions, you can ask them via the chat or you can send me an email.